Rohra, and welcome to the third session of the chapter Refraction of Light at Curved Surfaces. Before we decide to do what we would be studying in this particular session, let us recall what we did in our second session. Let's begin with recollection of the chapter. So in our previous session, we did we summarized some rules for sign conventions for to measure the distances such as object distance, image distance, focal length for lenses. So for all purposes, we would say that distances would be measured from either the pole or the optical center. Usually I would say keep your object to the left of the lens, and then you say that the direction of incident light would be the direction in which you measure the distances as positive, and the direction of incident light opposite to which would be the negative distances. Distances measured would be distances that would be measured vertically above the principal axis would be as positive, whereas distances that you measure vertically below the principal axis would be as negative. We studied the curved surface formula for refraction that tells you the relationship between the refractive indices and the object distance, image distance, and radius of curvature of a given material. And now we came to those surfaces which have two surfaces together joined, and we have one material in between of them, and those substances are lenses. And lens is formed when a transparent material is bound with two surfaces. So if you want to see a demonstration, then this is your material inside, and it is bound by this surface here and this surface here. So these are two surfaces, and this is the transparent material they are talking about. So this is your lens, and this is the two surface they are bounded by. And till now we have been discussing everything taking that the radius of these two surfaces, radii of curvature of these two surfaces is same. Here we will see one place where it's not always true that the radii of these two surfaces that you are seeing is going to be the same. Sometimes it's going to be different. For example, plano-concave lens or plano-convex lens or convexo-concave lenses. Such as lenses like here, this is one concave lens, and you have a convex lens. So lens like that, the radii of this surface that you have plus the radii of this surface, it's not going to be the same. Maybe it's going to be different, and for such cases you will have a formula that's going to differ from this curved surface formula. You will have two radii, and then for if you want such a lens, then what is the perfect focal length that you should select for such a particular lens? We will check all of this, and we will study. So we have right now, we've discussed image formation for we have not discussed the image formation, but we have discussed how rays of light behave with biconcave and biconvex lenses, and from there we have taken lenses whose radii have been whose surfaces, both surfaces have equal radii. That will not happen later. Then we studied about the definitions that are relating to our lenses. We studied about optical center, we have studied about center of curvature, we have studied about radii of curvature, we have studied about principal axis, and we have studied about principal focus. Let's go to them one by one. First is optical center, center point of a lens. Its optical center, it is also called origin. It is represented by O, and optical center of the lens is which any ray that comes through this point will go undeviated. Then we have two centers of curvature, which is the two centers of the imaginary spheres of which the lenses are a part of. Then we have radii of curvature, which are the radii of the two imaginary sphere of which the lenses are a part of. Till here, all the rays that we took, we saw that the center of curvatures of both of them were equal, hence the radii were also equal. Principal axis is the imaginary line that will join the two center of curvatures of the lenses. Then we have two principal focuses, as I told you, and then we have focal length, that is the distance between the focus and the optical center. Then we have aperture, which is the effective diameter of the circular outline. And then we studied behavior of certain light rays incident on lenses. The 4 rays that we studied were rays which are parallel to principal axis after refraction either appear to be coming from focus or pass through focus. Rays passing through or directed to the focus, they emerge parallel after refraction, or the third one is that rays directed to optical center, they go undeviated. Rays passing along principal axis also go undeviated. Now, in this particular session, we are going to study some rules that we have to follow, that according to which we will be drawing ray diagrams for image formation by both convex lenses and concave lenses. Then we will come to image formation by convex lens, then we will come to image formation by concave lens. Then we will derive the lens formula that will relate your image distance, object distance and the focal length. Then we will come to another term called magnification. This is the term that we have already studied in the reflection chapter. Then I will tell you another formula, which is lens maker's formula. That lens maker's formula, according to its name, helps you define a lens of a different kind. So a lens has two surfaces. One surface has one radii, one surface has one radii, and you have two medium that separates them, right? One would be some medium and the other would be some medium. If you have to draw a certain, if you have to make a certain lens of a certain given focal length, how are you supposed to define that particular length, focal length? How are you going to relate it to the refractive indices and the two radii if they are not same? So this is what lens maker's formula tells you, and that the derivation we will see. Numericals, I think we will discuss in the next session when we discuss question and answers. Then we will make a summary of what we did in the entire session, and then we would recall the chapter refraction at curved surfaces. So let's begin by the rules to draw diagrams for image formation by lenses. These are the given set of rules that you use, that you will use to draw ray diagrams for image formation. So for drawing a ray diagram to find position and size of the image formed, usually the two important parts of whenever you're drawing a labeled ray diagram, it is to find object position or image position, or you have to find the size of the image, or you have to say the nature of what the image is. So you need to follow the rules that are mentioned below. You either select a point on the object which is placed on the principal axis. So if you have a principal axis, you will select a point on it, and then this point will act as your object. You will draw this object of yours. If this is your lens, then I always advise to keep your object on the left side of the lens. Now you choose a point. Now you choose any two rays that are given to you by the 4 rays that we discussed. Any 2-ray interaction will give you an intersection point, and that intersection point can be your image. So let's take one ray that is going to pass undeviated through the optical center. Let's take one ray that is going through your focus, or let's take one ray which is parallel to your principal axis. This is your ray, it's parallel to principal axis. After reflection, it will go and pass through focus. Let's say this point is focus. For right now, we don't know. Let's say this point is focus. All I'm telling you is the rules. You have to take 2 rays, and the intersection of those 2 rays, here is the point of intersection. This will give you the image, and that intersection will act as the head of the object, and this will be your image formed. So you have to extend both rays to intersect at a point, and this point will give you the position of the image. From the point of intersection, you can draw the normal to principal axis, and then the length of this normal will represent the size of the image. So this is the normal we are talking about. This is the principal axis, this is the normal, means a perpendicular, and this will be the size of the image. This is the size of the object, and this will be the size of the image. So any situations that you took that we have discussed before, one ray parallel to principal axis, ray passing undeviated, ray passing through just ray which is along the principal axis, ray which is passing through focus, maybe after reflection it will become parallel to principal axis. Any of those rays, you can take any situation that you want, and any of those 2 rays intersection will give you the image that you will form. This is the case of convex. We will discuss a lot of cases for convex lens, concave lenses, and you will see the image formations. Now, image formation by convex lens, and now we begin the image formations. I have told you the basics. If you want, you can take both the image by this particular diagram where you have to show this lens, or you can just draw your basic arrow like this. Both of them will do, but what you have to show is show both center of curvatures, you have to show both foci, and you have to show optical center if you're drawing this diagram. If you are drawing this diagram, I don't think it is very necessary to show the optical center. If you want, you can, but I suggest you label everything. In both cases, it is necessary to show everything. And hence you have this. Now the first position that we always take is object at a very far distance, and that far distance usually means that the object is at infinity. It's not that the object is at a finite at a distance that you can never see. It's not somewhere near the sun, but sun is also very far away as compared to the setup that we have. So that to mention that distance, we say that it is at infinity. So because we have to say that rays that will be coming from an object that is so far away will be nothing but parallel. So any rays that come from a very far away object, which is the object position of infinity, will be parallel. So you have parallel rays to your lens. And you know that for a convex lens, if the rays are coming parallel, after refraction, they will pass through focus on the other side. So focus on the other side, all rays will point through the focus. So the image actually is formed here, but the image is it's a very pointed image. It's a point size image. The image is so small that we call it point size image. And that point size image is real. It is inverted. If you want to see, this image would be something like on this particular, and it would be like this. So this image is inverted. It is real, since it is formed by the actual intersection of refracted rays, and hence this image is real. It will be inverted, but it will be extremely small as compared to that particular object which is at a very far away distance. And hence we say that if the object position is at infinity, the lines coming here, the rays coming here would be parallel. After refraction would pass through focus, and hence this is the image that would be formed. So if the object position is at infinity, image position is at f1, it is real, inverted, and extremely diminished. Next, image position by convex lenses, object is beyond center of curvature. So here in the first case also, object was beyond the first center of curvature, right? Or the second center of curvature in your case. It was beyond this center of curvature, but it was at a very far distance. It could not be represented on this principal axis. This time we have an object which is clearly more near to us, and hence we say that this object is at a finite distance. So if you take this object, you have this object, it is at a finite distance. You have this pointer head. From here you have one ray which is going directly to the optical center, so it will go undeviated. Second ray is traveling parallel to principal axis, so after refraction it goes and it passes through focus, and you have the second ray. Intersection point of these two rays is here. If you see the red dot, this is the intersection point of these two rays. Since this is the intersection point, this is the image where image head will take place. If you draw normal from this point to the principal axis, this will be the size of the image. So when the object is beyond your center of curvature, the image will be formed between focus and center of curvature on the other side of the lens. Since it is formed on the other side of the lens and it is formed by actual intersection of refracted rays, it is a real image. It is inverted, but if you see this length of this object and the length of this image, it is diminished. It is smaller in size, so hence we call it diminished. So when the object is beyond center of curvature on the first side, image is formed between the focus and center of curvature on the other side. It is real, inverted, and diminished. Next case. object position now is exactly at center of curvature. So if you see, we are moving the object slowly towards the lens, and now you have kept the object at exact center of curvature. And now you draw two rays. First one, again you take, the most common ones are these ones that is parallel to principal axis and one that goes undeviated through origin. So if you take the first one, it goes undeviated through the origin. Second ray, it goes parallel to principal axis, after refraction passes through focus on the other side. Wherever they will meet, you will see that that point, when you extend it to principal axis, that point will be C1. So what is happening is, if the object position is at C2, image position is also at the center of curvature, but it is on the other side. The image will be real, the image will be inverted, but the image size will be the same size as that of the object. So if the object position is at the center of curvature, the image position will also be at the center of curvature, and it will be real, inverted, same size as that of the object on the other side of the convex lens. Let's go to the next position. You have image formation by convex lens. Now you have object between center of curvature and focus. You have now the object position a bit closer to the lens. So now you have again the same two rays. You take the first ray, which is traveling parallel to principal axis, after refraction becomes a point, and it passes through the focus. Second one is the one that will go undeviated through your optical center. This time if you see, the image position is beyond center of curvature on the other side of the lens. Beyond center of curvature on the other side of the lens, the image is real, the image is inverted, but in fact when you move the object between center of curvature and focus, the image size increases. So the image is magnified. We say the size of the image is greater than the size of the object, hence we say that the image is magnified. So this is the case when the object position is between center of curvature and focus. The image position is beyond center of curvature on the other side of the lens. I think when you are asked in the examinations image positions for lenses, if the image is real and if it is, you have to check whether it is on the same side of the lens, because you are going to see virtual images that are going to be formed on the same side of the lens. And since you have two centers of curvatures, two foci, you have to mention where the image is being formed, on the other side of the lens or on the previous side of the lens. Anyway, the image is real, inverted and magnified. Let's go to the next position. Object now is at focal point. You know, when object was at infinity and all the parallel rays were coming, we saw that the object formed a point size image at the focus. This was the very first one we saw. And the opposite is what going to happen here. Now the object is placed at the focus, and now if you take rays, one that goes undeviated, other that goes parallel to principal axis, after refraction passes through focus, you see that the images will meet, but they will be at a very far distance. Hence we say that the image will be formed, but it will be formed at infinity. Let's say that they do meet at some point, if you here, and this point, let's say, is very far away. So suppose they meet here. So actually they are meeting and the image is being formed somewhere here. So the object, when it is at focal point, the image is somewhere at infinity, even beyond this distance that I have made. I cannot shift the slide anymore. So the image position when the object is placed at the focal point is at infinity on the other side of the lens. You have to mention that it is on the other side of the lens. The image is real, it is inverted and it is magnified. Let's go to the next position. We have the object now between the lens and the focal point. This is your object. This is not the object, this is the image. This is your object. Here. This is the object, and now you have to take the same two rays. The first one that will go through optical center and it will go undeviated. Second one goes parallel to principal axis and after refraction it will pass through focus. If you go and you see that they are being extended on the other side, since they do not meet here, they are diverging. After the object passes the focal point, rays start to diverge, refracted rays start to diverge. So if you extend them this side, you see that they don't tend to meet. But if you extend them on the opposite side, you see that they come and they meet at a point. And that point is the point where the image is formed. So this is the place where the image is formed. So this time the image is on the same side as that of the object, and the rays are not actually meeting, they are appearing to meet because we are extending them backwards. So the position of image is on the same side as that of the object when object is between your lens optical center and focal point. So the image this time is virtual, it is erect, and it is magnified. It's magnified since the size of the image is greater than the size of the object. It is virtual since the image refracted rays are not actually meeting, they are appearing to meet. So when the object is between lens and focal point, the position of image is on the same side as that of the object. Virtual, erect, and magnified image is formed. These were the cases for image formation by convex lenses. We have 6 cases and we have studied all of them. For image formation by concave lens, actually there is not really a case to study, because in every case wherever you place the object, you will find that the image that it will form will be virtually erect and highly diminished. There will be absolutely no other property of the image that comes through concave lenses. Concave lenses always form virtual, erect, and highly diminished images. But still, just for the case of simplicity, I will divide them into 2 parts. One, when the object is at infinity, that is the first case, so rays are coming from infinity, and the second case when rays are anywhere between the infinite distance and optical center. Anywhere between infinite distance and this optical center, if you keep the object anywhere, you will see a virtually erect and highly diminished image. Why am I separating these two? Because this particular time object, the image is virtual, it is erect, it is diminished, but it is formed at focus. So it is formed at the focus. So if rays, if you see, they are coming from infinity, and after refraction they are diverging. If you appear to extend them in the opposite direction, they are appearing to be coming from the focus. As you saw, paraxial rays do that. And hence, we say that the image is formed at focus. But the thing is that the image here is virtual, erect, and magnified. Actually, it is not this huge. But the image is virtual, it is erect, it's highly diminished. As compared to some object that would be like here, it's huge, and parallel rays are coming here directly. Let's say these are parallel rays that are coming. So the image is formed here. It is on the same side as that of the lens as that of the object image, and it is formed at the focus. It is virtual, it is erect, and it is highly diminished. So here we are at the second position, where if you keep your object at anywhere between infinity and pole, then you will have the image position as between the focus and optical center on the same side of the lens as the object. And the image that will be formed will be virtual, erect, and it will be diminished. So anywhere, so if the object is somewhere here, this is in case of infinity, and this is your optical center. Anywhere between these two positions, if you keep your object, you will always get an image which is virtual, erect, and it is diminished. So we say that the object is at a finite distance anywhere between infinity and the optical center of a concave lens, and after that, anywhere you place this object on this particular distance, the image will be formed between the focus and the pole of the focus and the optical center of the lens. It will be on the same side as that of the object. As you see here, the object that is there is also on the left hand side, and so is the image. So the first ray that you take is the ray that goes undeviated. The second ray that you take is traveling parallel to principal axis, and after reflection diverges from the lens. The refracted ray diverges. it is not going to converge. This is not a convex lens, so parallel rays after refraction will not go and pass through f2. This is a wrong drawing. It's a wrong ray diagram. Since concave lenses are divergent lenses, we have to consider that fact and see that parallel rays of light after reflection will diverge. But if you extend it on the other side, then it will appear to be coming from the focus, and this ray, when interacts with the ray that goes undeviated, you will see the intersection will form an image, and this intersection is where the virtual image is formed. So when image formation by concave lens, actually anywhere you keep it, even if you keep it at infinity and the image is being formed at the focus of the lens on the same side, the image is going to be virtual, it's going to be erect, and it's going to be diminished. That is why sometimes in general we say that we only have one case for our concave lenses, that is, you keep the object anywhere between infinity and optical center, you will always have the image as virtual, erect, and diminished. So this was the last case when we are relating to image formation by concave lenses. Now, lens formula. Now that we have come to the conclusion of both image formation by convex lenses and image formation by concave lenses, we are going to study the formula that is going to relate your image distance, object distance, and your focal length. In this particular case, your image distance is PO. PO is U. This is U. This distance is U. Pi is the distance that is your image distance, and that is V. While Pf1 is the distance which is focal length f. We are trying to relate the distances between them and find a relation between them. So now these are line segments and we need a relation between these line segments. So what we are going to do again, we are going to find similarity between two very specific triangles, and from those triangles we will derive the ratios, and from these ratios of the line segments we will be able to find an equation which will relate U, V, and F. So for this particular point we have taken a convex lens, a case of a convex lens. So this is your convex lens, this is your object O. The object O has rays, one that goes undeviated from the optical center, second that goes parallel to principal axis, after which after refraction it passes through focus. They both meet at point I dash, and this is the point where the image is formed. As you see, I dash is the image that is being formed. So now we have I dash, we have O dash, we have object distance, we have image distance, and we have focus. So now we are going to relate all of them using similarity of triangles. Let's go and do this. So we have PO, which is object distance, we have PI, which is image distance, and we have PF1, which is the focal length. Let me now take you to the triangles which are similar. The first triangle that you will see that is going to be similar is this triangle. F1, P dash F1. This is the first triangle, and the second triangle that you're going to see is right opposite to it. It is F1 I dash I. This is the triangle that's going to be similar to our triangles. So you can clearly see these two triangles are the triangles we are trying to find a similarity between. Why are we choosing these two triangles? Because these two triangles contain Pi, which is image distance, they contain Pf1, which is focal length, and they contain the height of the image. This is the height of the image, I dash. So let's try and find similarity. First two angles are vertically opposite angles and they are equal. Second angle that you see is the right angles that are equal. Now the third angle automatically becomes equal. So we know that by AAA triangle similarity, we have triangle P dash P F1 and triangle F1 I dash I as similar. If we know these similarities, we can say that P dash will be divided by I dash. So the two straight lines will divide each other and will be equal to the ratio of Pf1 divided by F1I. Pf1 and F1I. Let me show this to you by a laser. This is P dash P. This is I dash I. This ratio will be equal to Pf1 divided by F1I. These two ratios are what we are going to find equal. Now what is happening here is that we can write F1 as Pi minus Pf1. Look at the diagram that is in front of you and see if this is correct. You can write F1I as Pi minus Pf1. Why are we doing this? We are doing this because F1I is a line segment we do not need. But Pi is the line segment we need and Pf1 is the line segment we need. So here is from the figure you get F1I equal to P1 minus Pf1. And if you substitute this value of F1 right in the first equation here, then you will get this equation right here. P dash divided by I dash equal to Pf1 divided by Pi minus Pf1. We just did we substitute the value of F1I as Pi minus Pf1. This is our second equation. This you must keep in mind. This is an important equation. Here, this is an important equation. Let us now find a triangle which contains our object distance and image distance and try and find the similarity between them. Let me tell you which one of them are going to be the ones that we are going to now find similar. The first triangle that we are going to look at is O dash OP. This triangle O dash OP. This is the first triangle and the second triangle is here, which is Pi dash. It's a bigger triangle. I hope you can see them. The first both of them have been marked in yellow. Those two triangles are the triangles that we are going to find similarity between now. Triangle O dash OP and triangle Pi dash I. Let's see how we find the similarity. The first one are vertically opposite angles right here. Second one is the right angle here and again the same right angle that we used for the red one here. Both of these right angles are equal and the third angle automatically becomes equal. Since the third angle automatically becomes equal, we have triangle O dash OP, which is here, triangle O dash OP, similar to triangle Pi dash. When you find this, you can basically have the ratio. This ratio you're going to get O dash O divided by I dash I is going to give you PO divided by PI. This is the ratio that you're going to get. This ratio is written right here. O dash divided by I dash is going to give you PO divided by PI. Why are we taking this triangle? Because O dash is the object height. PO is the object distance. Pi is the image distance. Now we know that O dash from this rectangle, look at these 4 points, O dash, P and O. These are forming a rectangle and from this rectangle you can see that O dash is equal to P dash P. So what you have to do is just substitute the value of O dash in equation 2. So you know O dash is P dash. You substitute this value right here and hence you will get this equation, pp dash divided by I dash equal to po by pi. So you have pp dash divided by I dash equal to po by pi, and you have pp dash divided by I dash equal to pf1 divided by pi minus pf1. So you see what is common here? Two things are common here. Here is p dash p divided by I dash, and here is p dash p divided by I dash. So you can equate them, and once you equate them from second equation and third equation, you are going to get this particular statement, which is po by pi equal to pi by pf1 minus 1. Or actually what you are going to get is pf1 divided by pi minus pf1. So let me write it for you here, right here. What you're going to get? You're going to get po divided by pi. From second and third equation, you have this pf1 divided by pi minus pf1. So if you divide the entire equation by pi, you will get 1 by po plus 1 by pi, which is equal to 1 by pf1. Please don't worry about these question marks. These are just font problems. So what you're going to get is 1 by po plus 1 by pi equal to 1 by pf1 if you divide the entire equation by pi. So now what is po? po is object distance. Here, what is pi? pi is image distance. Right here. And what is pf1? Here is pf1 and it is focal length. So now if you have to convert 1 by po plus 1 by pi equal to 1 by pf1 into a general equation, you need to use sign convention. So according to sign convention, we say this is the side that is going to be negative, this is the side which is going to be positive, and we do that. So that makes po minus u, pi as v, and pf1 as f. Here it's written pf1f, pi v, po as minus u. If you substitute this value in the equation 1 by po plus 1 by pi plus 1 by po equal to 1 by pf1, you will get 1 by v minus 1 by u equal to 1 by f. And this is the lens formula. This relates image distance with object distance, and both of them you relate it to the focal length of the lens. This is the formula that is valid for every lens, convex or concave, provided that you use the right sign convention. Now let's come to magnification. What is exactly magnification? Magnification tells you about the height of the object to the height of the image, or the ratio of height of the image to height of the object. What it is trying to tell you is how large the image is, or by what ratio has the image size increased, or by what ratio has the image size decreased. This is what it is trying to tell you. And you have to see how you're going to find these ratios and how can you relate these ratios to image distance and object distance. So let us find the two triangles that are going to be similar here also, and let us try to relate to them. So the two triangles that here we are going to see are OO-P. This is the first triangle, OO-P. It's marked with red, OO-P, and the second one that we are going to see is II-P. Both of them contain our object distance, image distance, object height and image height. If you look carefully, They contain I dash and O dash. I dash is the image height, O dash is the object height. They contain PO and PI, which is U and V respectively. So in the triangle you have II by PI is equal to OO by PO, right? This is the ratio that we get once we see that the triangles are similar. They are similar by AAA similarity. If you do not see the similarity, I will point out to you again. This is the vertically opposite angles. This is the right triangle. This is the right angle. And then we have the third angle, which is automatically equal. And hence we can say that the triangles are similar by AAA similarity. Since we can say that the triangles are similar with AAA similarity, we are going to compare the ratios and say that II by PI is equal to OO by PO. Hence, if you cross multiply, you can write II by OO is equal to PI by PO. And once you write this, what is II? II is I dash is your H1 or HI, which is height of image. What is OO? O dash for you is the height of the object. What is PO? PO is U, and what is PI? PI is V. Once you get this, according to sign convention, you will get minus HI by H0 equal to minus V by U. If you cancel out the minus signs in both conditions, what you will get? You will get magnification as HI by H0, which is equal to the ratio of image distance to object distance. And this is magnification M. M magnification is represented by ratio of height of image to height of object, which is also equal to the ratio of image distance divided by object distance. This is how you get magnification. It is represented by small m. Let us now go to the next slide where we are going to study lens maker's formula. This is going to be a bit difficult, a bit harder than the previous lens formula and magnification. So try and pay attention, because here the refraction that is going to take place, it is going to take place twice. So let's see what we have. We have a convex lens with two sides, and we have a material behind, just inside it. This is the transparent material whose refractive index is NB. Then we have the surrounding refractive index, let's call it NA. We have a point O which is placed on the principal axis of a thin lens, and then we have a certain distances are marked. Now what you can see here is that radiuses are marked by R1 and R2. It means that here radiuses are, the radii is not equal. This is the radii of the first one, that is, let's call this A, side A. This curved surface, let's call it B, and B has radius R2 while side A has radius R1. Let me show it to you by marking it. This side is A, it has radius R1. This side is B, it has radius R2. And what we are seeing considering one ray that is going and is incident on A. Let's take the first one. It's incident on A, point A. And we have the other ray which is going undeviated from our optical center. Let's say they go and they meet at point Q. Here is your image formed for point Q. Point Q is your image, point O is your object, and you have the refraction taking place the first time here at point A. So let's go and explore this. You have image distance, which is V, but V here is equal to X. Your image distance is X because your image is formed at Q. You have radius of curvature as R1. You have N1, that is the first refractive index of surrounding medium as Na. You have the second refractive index, that is refractive index of the material, as Nb. So this time N1 equal to Na and N2 equal to Nb. We know that the curved surface formula says that N2 by V minus N1 by N1 by U equal to N2 minus N1 by R. Let's fill in the values. Our N2 is Nb, our N1 is Na, our V is X, our U is just U. N2 again is Nb and N1 is Na. So our equation becomes Nb by X plus Na by U equal to Nb minus Na by R1. This is the first time we are applying the curved surface formula. I told you refraction here will take place twice. So this is the first time the refraction is taking place at convex curved surface A. For this surface, here we have point object O. It is incident on point A. It refracts and then image is formed at point Q. When the second ray, we say it goes undeviated and it meets this first ray at point Q. Point Q is the image, point O is our object, and hence we get Nb by X plus Na by U equal to Nb minus Na by R1. This is our first equation, keep in mind. But now the ray has refracted, which is at A, suffers another refraction at B. Pay attention. This is curved surface B, and now this surface is a concave surface. The ray is incident on the surface which has an inward curving. This inward curving, and hence this is a concave surface. The image of Q will now act as the object, and this object will now have the image at I. Look carefully. The refracted ray, when it bends, it actually goes and refracts itself and forms the image at I. So we can say that the image of Q is formed at I. So if Q is the object, for our second case, when refraction is taking place at B, if Q is the object, then I is the image formed. So we can say I is the image of Q for the concave surface B. So this time our first refractive index is going to be Nb and our second refractive index is going to be Na. So that is what we are going to check. Object distance this time becomes X and image distance is Pi. Look carefully. This time our object is Q. Q is our object and the image of Q is formed at I, this point. So what is the object distance? This time is X. What is the image distance? It is V. What is the radius of curvature for this particular side when the second refraction is taking place? It is R2. So now for R2, for this ray, let's look at this ray that is undergoing refraction for the second time. This is the outer refractive index and this is the second refractive index this time. So N1 this time is Nb and N2 this time is Na. This is what has to be remembered. For the second case, N1 is Nb and N2 is Na. Here are these mentioned right in the paragraph. And now for the formula that we have for curved surface, we will substitute these values. So what we will get is Na by V minus Nb by X equal to Na minus Nb by minus R2. And once you get minus R2, you will see that the first equation and the second equation will get added. Once you add them, you will get Na by V plus Na by U equal to Nb minus Na multiplied by 1 by R1 plus 1 by R2. Divide the entire equation by Na and you will get 1 by V plus 1 by U equal to Nb divided by Na minus 1 whole multiplied by 1 by R1 plus 1 by R2. Now you know that Nb divided by NA is equal to NBA. This is what you can write: refractive index of the material with respect to surrounding medium. So the refractive index of the lens is NB and the surrounding medium is NA. So hence you can write NB divided by NA is equal to NBA. So that is what you can just put in the formula that was before, and you can say 1 by V plus 1 by U equal to NBA minus 1 whole multiplied by 1 by R1 plus 1 by R2. This is your equation, and it is called lens maker's formula, but it is not according to sign convention. Right now we have only derived this formula for a convex lens. Now if you want to make it a universal case, what you have to do is you have to apply sign convention. If you apply sign convention, U will become negative. So instead of plus U, you put minus U, and from there you will have this particular equation right here. 1 by V minus 1 by U equal to NBA minus 1 whole multiplied by 1 by R1 minus 1 by R2. But you know that 1 by V minus 1 by U is 1 by F. So what you do is here, where you have 1 by V minus 1 by U at the end, you just substitute 1 by F. Once you substitute 1 by F, you will get 1 by F equal to NBA minus 1 multiplied by 1 by R1 minus 1 by R2, and this is lens maker's formula. What lens maker's formula is telling you is that if you want a lens with two different kinds of surfaces, let's say first surface is A with radius R1, second surface is B with radius R2, and if you know the refractive index of the material, which is NB, and if you know the refractive index of the surrounding medium, you can make a lens of a given focal length, whatever focal length you want. So you can make a lens of a given focal length, and once you have that, you can design different lenses. This is the formula that is used for designing lenses. If the surrounding medium is air, I told you already that N by B divided by N by A is equal to NBA. Now if this is 1, NBA, if NBA is equal to 1, then you can just write that NBA is equal to NB, and hence the equation then will become 1 by F is equal to N minus 1 multiplied by 1 by R1 minus 1 by R2. This lens maker's formula is used only when your lens is kept in air. So means your surrounding medium is air, and the surrounding medium refractive index is 1. That means the surrounding medium is air. So this is what lens maker's formula is used for. So that is it. Let us now discuss summary in the next slide. Let's discuss the summary of the session. We are going to discuss the rules that we are using to draw ray diagrams. You are basically selecting a point and you are fixing that point to be object O for you. So this is your entire, let's say, lens. This will be the point at which your object is there. Then you will draw two rays, any rays that you chose from the rays that I have mentioned before. So one of the rays that you can choose is the ray that goes undeviated from the optical center. Second ray, that can be that one that you draw parallel to principal axis and after reflection passes through focus. Wherever they interact, that point will be chosen as the head of the image. If you extend both rays to intersect at a point, that point gives you position of the image. After that, this normal is what they're talking about. If you draw this, it will give you the size of the image. Length of this normal will represent size of the image, and the length of this normal represents size of the object. Now, if the position of the object is at infinity for a convex lens, the position of image is focal point, and the characteristic is it's a point image, it is inverted, real and diminished. If it is beyond center of curvature, the position of image will be between focus and center of curvature on the other side. The image will be inverted, diminished, and real. Next, if the particular object is being kept at center of curvature, then the position of image will also be on the center of curvature on the other side. The image will be inverted, but it will be same size of that of the object, and it will be a real image. If you keep now the image object closer to the lens, and now you bring the object between focus and center of curvature, the image will be formed beyond center of curvature on the other side. It will be inverted, magnified, and real. If you keep the object at focus, image will be formed at infinity. If you now keep the object between focus and pole or optical center, then the image formed will be beyond focus, but it will be on the same side as that of the lens, and it will be virtual, erect, and magnified. For concave lens, irrespective of position of the object on the principal axis, you will get an erect, virtual, and highly diminished in size the image will be, and it will be between focal point and optical center of the concave lens. Lens formula that we derived was given as 1 by v minus 1 by u give you 1 by f. That relates your object in distance with image distance with the focal length of the lens that you're using. Magnification M is defined by the height of the image, ratio of height of image to height of object, which is the same as ratio of height distance image with distance object. Lens maker's formula gives you, if the refractive index, surrounding refractive index is air, then the lens maker's formula is 1 by f equal to n minus 1 multiplied by 1 by r1 minus 1 by r2. Lens maker's formula helps you make a certain lens with a given focal length if you know the refractive indices of the surrounding mediums and the radius of curvatures of the materials that you are using. This particular formula can only be used if lens is kept in air. If lens is not kept in air, then the formula becomes 1 by f equal to nBa, which is refractive index of the lens divided by refractive index of the surrounding medium multiplied by 1 by r1 minus 1 by r2. Let's now recall the entire chapter, refraction of light at curved surfaces. We know that change in path of light ray as it passes from one medium to another is called refraction of light. Refraction takes place not only in light but also in other waves such as sound waves. So in physics, refraction is the change in direction of a wave as it passes from one medium to another, or you can say a gradual change in medium. Refraction is the most commonly observed phenomenon. When light travels from a denser to a rarer medium, it bends towards the normal. When light travels from a denser to a rarer to a denser medium, it bends towards the normal. While light travels from a denser to rarer medium, light bends away from the normal. If I am to show you, this is a particular slab where your light ray is incident, and this is your normal. If it is going from rarer to denser medium, light will bend towards the normal. If it is going from a denser medium to a rarer medium, light will bend away from the normal. Causes of refraction is because speed of light differs for every media, and the speed of light is less in denser medium while more in rarer medium, and hence whenever the speed of light reduces, whenever it tries to bend towards the normal. When the speed of light increases, it tends to bend away from the normal. This is something you must remember. I is angle of incidence, R is angle of refraction, and E is angle of emergence. Now, refraction of light occurs according to the following laws. 1. The incident ray, refracted ray, and normal to the interface of two media, they all lie on the same plane. And the second is the Snell's law of refraction, that is the ratio of sine of angle of incidence to sine of angle of refraction of a light of a given color is constant, which is mu, which is equal to refractive index of 1 divided by refractive index of the second medium, which is n1 by n2. Next, the sign conventions that you use when you are trying to make the lens formula or even the curved surface formula for your object image distances, then you will say that all distances are either measured from the pole or the optical center. Distances measured along the direction of incident ray will be taken as positive. Distance measured opposite to the direction of incident light will be taken as negative. Height measured vertically above will be positive, and height measured vertically below will be negative. And this is the curved surface formula, which will help you relate your radius of curvature with object distance, image distance, with the refractive indices of the material. This is the curved surface refraction formula. Now, you know what a lens is. A lens is formed when transparent material is bound by two refracting surfaces. This is your transparent material, TM, transparent material. Lenses can be of various kinds: biconvex, biconcave, plano-convex, plano-concave, concavo-convex, and convexo-concave. This one is called a biconvex, while this one is a biconcave. Or a biconcave is just concave, and a biconvex is just convex. Now, optical center, the definitions that are relating to our lenses. Optical center is the center of the lens. And we have center of curvatures, which are two centers of imaginary spheres of which the lenses are a part of. Radii of curvature would again be the radius of the two imaginary spheres of which the lens is a part of. If this is focus, then this is center of curvature, but you have to mark them both sides. Then you have principal axis. This is the imaginary line that is joining your center of curvatures to your optical center. Principal focus are two, this first one and the second one. Then you have focal length, which is the distance between the focus and optical center. Then you have aperture, which is basically the effective diameter of the circular outline of the spherical lens. Now, we know that certain light rays behavior we can predict. We know the ones that travel parallel to principal axis, those ones are the ones who will, after refraction, they will become and they will pass through the focus. This is your lens. Then you know that ray directed through optical center. This is your optical center, let's say. Then the rays that are directed to optical center will pass undeviated. Then the rays that pass through principal axis will also go undeviated. Those that now come through the focus after reflection, if they are coming through focus after refraction, they will become parallel to principal axis. There are rules that you are choosing when you are trying to draw ray diagrams. You are selecting a position from where you will point your object. This will be the object, after which you will choose two rays which will determine where the image will interact. This is your lens. This is the entire, let's say, a principal axis. Two rays you select. One may be parallel to principal axis, after refraction becomes passing through focus. One that goes undeviated. These two rays, if you select, these are the most common ones. They help you draw image diagrams very easily. And once you draw the image point, you just draw normal to your principal axis, and that will show your size of image. Next, now you see the images that are formed by convex lens. We have already discussed the position of object, image, and characteristics. If it is at infinity, then we know that the focal point is where the position of image will be. Point image will be real, inverted, and diminished. If it is beyond center of curvature, it will be between focus and center of curvature on the other side. If it is at center of curvature, the image will also be at center of curvature but on the other side. If it is between focus and center of curvature, it will be beyond center of curvature on the other side. If the object is at focus, the image will be formed at a very far away place. We call it infinity. Image will be inverted, real, but it will be magnified. If you keep the object between focus and optical center, then the image will be formed beyond focus, but it will be on the same side of the lens. Virtual, erect, and magnified. For concave lens, irrespective of where you keep it, you will always get an erect, you will always get a virtual, and you will always get a diminished image. And the lens formula that now relates your image distance, object distance, and with the most important case, that is your focal length, f, is this: 1 by v minus 1 by u equal to 1 by f. And the magnification of such a setup is defined by the fact that height of image divided by height of object, or the ratio of height of image to height of object, is equal to v by u. Lens maker's formula is a formula that helps you see whether you can basically make another kind of lens with a certain focal length if you know the refractive indices of the surrounding medium and of the lens, and if you know the radii of curvature of both the surfaces. This is only used when lens is kept in air, while otherwise you use the formula 1 by f equal to n BA, where BA are basically the refractive index of the material divided by refractive index of surrounding medium. This is all for the entire session of the refractive chapter, refraction of light at curved surfaces, and even if it is for the entire chapter, refraction of light at curved surfaces. So I hope the basics have again been cleared, and I hope the formulas now are clear. There is one that we have is lens formula, one we have lens maker's formula, and one is curved surface formula, and we get the lens maker's formula through curved surface formula only. You have to remember all formulae, and you have to keep in mind the sign conventions, otherwise you will make mistakes during numericals. The numericals will be discussed with you, the ones that are in the book, when I am discussing with you the question answers. I will add some extra numericals so that you are able to understand the formulas better. So until this is then, I hope everybody is safe. So until we meet next time, thank you and goodbye.